one Euler, then you'll do an inverse R31 of the R3 Okay. Depends upon how you want to represent your orientation. If you want to represent it in terms of 3 Euler angles, we do what we did last time, like because symbolically we did it, but you can, this will be a numerical matrix, and you can substitute that. So basically, let's say that I have a equation like this. So this will be orientation. So I have this equation, right? I have the forward kinematic equation. Let's only take x, y, and z. Now I can find the position of the end effector at any given instant of time. So if I'll say find the position of end effector when theta 1 is 30 degrees and theta 2 is, let's say, negative 90. I'll substitute this in here, I can get my positions because I know theta 1, theta 2, I can find x, y, and z. It's simple as that. If I know theta 1, theta 2, I can find my orientation because I'll have a numerical matrix for this. All of this will become definite values as soon as you substitute theta. So this will give me a relation. I can find PD if I have a function of Q. Okay? This is a function of Q. Q is the set of joint angles, which is theta 1, theta 2, theta 3, and so on. So once I have a relation between the joint angles and the position and the orientation of an end effector, I can easily find it out. So this is your forward kinematic relation. Let's take a different manipulator, a slightly different manipulator, and you can tell me what you get for this. Let's say all right, let's do this. So this is theta 1. This distance is given as 1. From here to here is d2. Okay. And from this point to this point is 1. Okay, and from here to here is d3. All right, we need to find d. Let's set up the dh table first. So this is a 3 degree of freedom manipulator. So first thing is you need to establish the z-axis. Let's finish the z-axis first. So you have z0 because this is a revolute joint. It's about the axis of rotation. This is the translation. This is a rotational prismatic joint, not a rotational joint. So this will be z2. I'm sorry, z1. Here, this will be z2. So we can complete the frame. We can say that this is, I'm going to say this is y naught, so this will make it x naught. All right. Now I want you guys to finish the frame. Set up the other two x-axis. So you need to set up three x-axis. One here, O1, O2, and O3. Now, the two axes are parallel. When the two axes are parallel, you have a choice to pick origin anywhere you like. So basically, along this line, you can pick the origin wherever you like for the second point. So let's say because we have defined it till here, I'm going to pick O1 here. So this is x1 like this. I'm going to pick this point as O1 because we know the distance, right? Makes it easier. Now I can pick x1 perpendicular to both of these. So I'm going to pick x1 like this. Okay. Finish this one. What happens when you have two intersecting z-axis? Where do you pick the origin? Point of intersection, exactly. This z2, z1 goes like this, z2 goes like this. So this will be O2. Okay. Now you want to pick x perpendicular to this. This is z1, right? z1 is going up. So perpendicular to this can be inside the board or outside the board. Let's pick that outside the board. x2. Similarly, we'll finish the third one here. All right, this is the end effector frame. Now you can write the table. Tell me what you get. A, alpha, D, theta. Now, this manipulator is a RPP because you have two prismatic joints, RPP manipulator. So this will be revolute, this is variable, D2 is variable because this is a prismatic joint and D3 is variable. Everything else we need to figure out. Any question about the choice of axis or the origin?
Professor, why we assumed that this is the z-axis? It can be, for example, the x-axis.
Which one, the z? Because the first thing that we said is, if you have a revolute joint, right, the z-axis is above the axis of rotation. This will be z. Okay, above the axis of rotation. So if I have a joint like this, that rotates like this, so this is my direction of rotation, so this will be the axis. Because I'm rotating like this, right? This is the direction of rotation. The curl of the fingers will represent the direction of rotation, and this is the positive direction of rotation. So this is the, okay?
Can I say, for example, I am rotating about the x-axis?
No, you cannot say you're rotating about the x-axis because the x-axis rotation is defined by theta. I'm sorry, x-axis rotation is this. This is the angle you measure between about xi, right? Theta is measured about zi minus 1. Okay, see, when you have, I'll explain this to you. So when you have the dx table, we are trying to measure rotations about two axes only. We have three axes, x, y, and z. Y is just a dummy axis, we don't use y. Okay? We use x to measure the angle between two z-axes, zi minus 1 and zi. This angle is called alpha, which is the joint twist. We use the z-axis to measure the angle between two x-axes. We call it the joint displacement. Okay? So always whenever you measure an angle measurement can only happen about a perpendicular axis. Okay, so if I have to measure between these two, I have to pick a perpendicular axis to measure the angle because the rotation is happening about this. Okay, so we standardize one axis, which is the z-axis. So if you have a rotation like this, so we'll say this rotation is theta. That means the angle between these two x. Because when I rotate this, what will happen is this x will rotate, right?
Yeah.
Like this. So this will change. This is fixed. So the angle between these two will keep on changing. So this is theta. Okay? That is the angle theta. When this one rotates, theta 1 rotates. If it becomes 90, this will, from the perpendicular of the board, it will go like this. So that will be 90 degrees. All right, let's fill out the table. What is A1?
0.
0, because A1 you'll measure about xi, distance along xi, right? Will come here. This is distance along xi. So if you're moving along x1, x1, until it intersects with the previous z-axis. The z-axis is meeting it at the origin, so this will be 0. Same thing here. A2 will be distance along x2 till it is intersected by x1. x1 meets exactly at O2, so this will be 0. Okay, let's go here. This will be distance along x3, this is O3. So Z2 is meeting it exactly, intersecting it here, so this will also be 0. Okay. Now, how do we measure alpha? What is alpha 1? Huh?
0.
0. Because both of them are parallel. Alpha is the angle measured about xi between zi minus 1 to zi. Okay? You measure from zi minus 1, you measure about xi. So in this case, both of them are collinear. This is z0 and this is z1. You have x1 here. So this is 0. All right. How about alpha 2?
0. Oh, I'm sorry. 0.
Okay, so
9.
here you have z1. This is z2. This is your origin. Right? At this point, O2 comes in. And you have x2, like this. So if I rotate like this, I'm going in the opposite direction. I should actually be going like this, from this axis to this axis, which is opposite, so this will be minus 90. Okay, so we'll write this as minus 90 or minus pi by 2. Okay, this is alpha 2. This is alpha 1, which is 0. All right, now here, once again, these two, Z3 and Z2 are collinear. This is Z3, this is Z2. Both of them are collinear, and this is X3. So alpha 3 will be equal to 0 degree. Okay. How about D1? How much is D1? 1. You measure along Z0. D1 is measured along Z0. Zi minus 1. In this case, for the first one is Z0. Okay. So this distance from here, O0, all the way up till it meets X1 is 1 unit. So this is going to be 1. How about D2? D2 is D2, right? Because this is variable, this is D2. Okay. How about D3? Huh? D3 is measured along Z2 because D3, if you want to measure this is measured along 3 minus 1 along Z2 axis. So you start from here, Z2, till it is intersecting the next axis. So Z2 starts from O2 till it intersected by X3 here. So this will be 1 plus D3. Because it's starting from here, Z2 is starting from here, all the way till it meets the x-axis. So this will be D3 plus 1. Okay? Otherwise you lose this unit if it's only D3. Okay? This whole thing is D3. This is what this is. Okay, let's talk about
Professor, do we need to put the D3 since D3 is a constant? Do we need to put the plus 1?
D3 is not a constant, D3 is a variable, this is a prismatic joint.
I mean, it alternates, so.
It alternates, but it has an offset of 1. So basically, if D3 is 2 units, the actual displacement of D2 will be 2 plus 1. You can take it as an offset, right? You're starting with the initial value, or constant initial value. So you can treat this part as an offset because your origin is here. Alright, so let's do this. So this is measured along Ti minus 1 between xi minus 1 to xi. Okay, so what is, this is a variable theta 1 as it is. What is theta 2? 0. And theta 3? 0. Both, all of them are parallel. All the x-axis are parallel, so they'll be all 0. So now what you can do is, from here you will generate 3 tables. A1, A2, A3. Okay, A1, A2, A3. So T03 will be equal to A1 times A2 times A3. So once you do this, you'll have a forward kinematic equation. Obviously, the first one, this is a rotation about z, so A1 should be pretty straightforward. A1 should not be a problem. A1 will be A1 is 0, so this will be 0. D is 1, so this will be 0. And this will be 1. I think there is a DI. DI is supposed to be 1. DI is 1. Okay, please do A2 and A3. Okay, let's do one question with a standard manipulator, which has 4 degrees of freedom. You can set this up and then I'll write it on the board if somebody is finding this out. In the meanwhile, let me draw this. Okay, if somebody has done this, just tell me these row wise. Somebody has that or no?
It will be 1 0 0 0.
Like this,
Yeah.
1,
0
0,
0
1.
0 0 0 1 0.
What do you mean 0 minus 1? Oh, there has to be D2, okay. 0, uh, uh, D2, okay, good. Yeah. And this one? This one will exactly be so you'll multiply those to get your matrix. Okay, so this manipulator structure is called, this is a 4 degree of freedom manipulator. It's called a SCARA. Which is, SCARA stands for selectively compliant assembly robotic arm. Okay, SCARA. It's a 4 degree of freedom. To be honest, it's called a 3.5 degrees of freedom because one of them is a repeat rotation, but anyways. So this will help you to move the end effector in any rotation, and this will fold from here. At the same time, it can go around. If you look at the top view of this workspace, you can have 2 concentric circles. It will track this space with any given, it's like a donut space, with any given rotation. You can approach it from the top with any given orientation like this. Okay. Anyways, so we need to find the forward kinematic equation for this. So let's set up the axis. I'll start with the simplest, which is the Z, and you can continue this on so that we can all agree upon a set of axes. So this is along this will be V2, V1, right? This displacement is along this direction, so I'm going to say this is Z2. Now, if you look at this is the axis of rotation, right? Because that is the direction in which it's a positive rotation, so this will be Z3. All right? Now, this displacement is D3. So, theta 1, theta 2, D3, theta 4. So, this is a R, R, P, R magnitude. First two are revolute joints, a prismatic joint, and then again a revolute joint. All right, so you can pick the axis. Let's say I'm going to set up the standard axis. Let's say this is my x0. Therefore, this will be y0. Actually, x0. So this is my thumb. Index finger is x. So my y-axis is wrong, right? Because when I put my thumb along this, we are using a right-handed frame of reference. X, y, x is along my index finger, this is my Z, and Y should be within the board. So this is the opposite, it should be within the board. All right.
Sir, can you repeat?
Okay, so if you have Z0 and X0 like this, right? You want to decide where is Y. Y has two options. It can be, Y first of all has to be perpendicular. These are all mutually perpendicular axes. So Y can be like this, or Y can be outside the board, right? It has two options. So which one do you pick? If you use your right-handed frame of reference, this is your thumb, is your Z-axis, that is X, and this would be into the board is the correct direction. Okay, this is the left-handed. If you're using the left-handed frame of reference, this will be Y. Okay, but in our case, we are using right-handed frame of reference, so this is the proper direction of Y.
So what's the difference between this and the first one? Because in the first example here we...
Nothing, I just switched it so that we can do it in any way possible,
so
right?
it's,
It has nothing to do, the eventual equation that you get will be the same. So let's say that your friend decides to use, instead of this, you decide to use it like this. That's fine, okay? You'll come up with different values for the angles, but when you multiply them and do the forward kinematic equation, this is unique. The final transformation that you get, no matter what DH table you have, will be the same, okay? These might not, the table might not be the same, okay? You can come up with a different table, but when you multiply them, the transformation is unique. All right, so now we need to fix here, these two are parallel, so Z0 is like this. Okay. What you'll do is, we'll have to pick X0 so that it intersects. So this is Z0, this is Z1. We can pick X1 like this, perpendicular to both and intersecting, or X1 like this. So let's say we choose X1 like so. Okay, so this will be at this point, this will be O1. Let's go here. Once again, you have two options. Because you have, if you look here, you have Z1 going up and Z2 downwards, right? X, you have to pick X2 such that it's perpendicular to both of them. We can pick X2 like this, or we can pick X2 like this. Okay, this is Z1, Z2. So what we'll do is try to keep it parallel so that some angles are 0. We'll take X2 like this. All right. Now, Z2 and Z3 are collinear. So you can have a choice to take x anywhere you want. Let's say I want to put this at this point. You can take it anywhere. If you put it here, then you have to account for this distance. Anyways, so let's say that this is, I'll take this exactly as x3, and this is O3. And I'll have here all right. Tell me if you have any questions about this, because this is a slightly different problem where you have anti-parallel z-axis. So I'm just going to have a certain distances marked out in case we need any of them here. Let's call this as A1. I'm going to call this distance as D1. Okay, we'll have to come with, let's say this is D6. Or let's call this as D4. In this case, a 4-degree of freedom. If you are ever confused about what axis you have picked is correct or not, just make sure that if these two rules are satisfied, you're good, okay? It need not have to be exactly the same as somebody else has done it, but so long as DH1 and DH2 are satisfied for every choice of x, then you're good, okay? These two have to be always satisfied. They need not necessarily be like how somebody else has done it. Okay, so here, let's write a DH for Scara. So this is RR, so this is going to be variable, this is variable. Okay, so now tell me what is